Hello everyone, this is Mona Asabari and I'm going to explain about pump system curves in a simple, clear way so that you will not forget it. Let's get started. We already know that pumps provide sufficient pressure to move the fluid through the system at the desired flow rate. And we use pump curves to know how much head is generated by the pump for a known amount of flow. And the pump curve is provided by the pump manufacturer. For system curves, it is nothing but the summation of all friction losses and the static head in the system. And this is usually determined by the engineer. The intersection between the two curves will give us an indication about the operating point. Most of us talk about pump curves and forget to talk about system curves. In fact, system curve is very critical. Why system curve is very important. Here we have a pump that transfers the fluid from tank 1 to tank 2. Imagine this scenario with me. I decided to add a heat exchanger at the discharge of this pump to meet the desired temperature. After adding the heat exchanger, what is going to happen to the system curve? The frictional losses are going to increase. So if I increase the frictional losses, then my system curve will be shifted to the left side. So will the operating point stay as it is? Obviously no. The system curve is shifted. Therefore, the operating point will be shifted to the left. So that's why the system curve is very important, and we need to understand how to develop a new system curve and check the adequacy of the existing pump. Is it going to deliver the same amount of head at the desired flow rate? We will know the answer after developing the new system curve. Now, what is the math behind the system curve? As you can see here, the curve is moving upwards and there is a y-intercept. This reminds me of parabolic equation that we studied back in school, where y is equal to mx squared plus c. In the y-axis, we have the head, and in the x-axis, we have the flow rate. Now the question is, what is the slope of the equation and what is there in the y-intercept? Let's find this out. The pump is the driving force which is going to move the fluid from tank 1 to tank 2, which is located at higher elevation. The pump needs to overcome all the type of resistance on its way, which is the friction energy in the piping and the difference in elevation between the two tanks. So the pump energy is equal to the friction energy plus the elevation energy. And if we convert the equation into head forms, then the head of the pump is equal to the losses head plus the static head. The cyclist here needs to go up to the hill, so she needs to overcome the elevation and the friction to move upwards. This reminds me of the first law of thermodynamics, where you can't get something for nothing. The law of conservative energy is applicable to Bernoulli's equation, so let's apply Bernoulli's principle to the pumping system here. In Bernoulli's equation, the summation of pressure energy, kinetic energy, and static energy is equal to constant. Since we have 2 points here, then the equation will become like this. P1 is the operating pressure in tank 1, V1 is the velocity of the fluid in tank 1, and H1 is the
elevation of the fluid in tank 1. Rho is the density of the fluid, and G is the gravitational force. We can convert this equation from pressure form to head form by dividing it by rho G. So the equation will be like this. There are two missing terms in the equation, so we need to add the head of the pump and we need to add the losses head. So this is the final form of the equation. Some terms in the equation can be neglected. Both of the tanks are exposed to the atmosphere, so the operating pressure is the same. Both are operated at atmospheric pressure, so we can neglect P1 and P2. The fluid in tank 1 and tank 2 is at rest, so the velocity will be 0, so we can neglect the kinetic energy head from both of the sides. Now, what we have left is the head of the pump is equal to the losses head plus H2 minus H1. H2 minus H1 is the static head. So how to find the static head? We need to find first the reference point. Our reference point here is the pump central line. So H1 is the liquid level in tank 1 with reference to the pump central line. And then H2 is the liquid level in tank 2 with reference to the pump central line. So the difference between the two will be the static head. So the head of the pump is equal to the losses head plus the static head. Now, the frictional losses in the system can be classified to major losses and minor losses. Major losses are because of the pipe friction, which is basically the interaction of the fluid with the pipe wall. The rougher the pipe, the higher the friction. And friction depends on the average velocity of the fluid within the pipe, the viscosity of the fluid, and it also depends on the pipe surface roughness. Now, for the minor losses, these losses are caused by pipe fittings, bends, and valves. If you have equipment in your piping system, then you can add the equipment losses, such as heat exchangers, strainers, and filters. These are going to cause frictional losses in the piping system. So the amount of energy required to overcome the total friction losses should be supplied by the pump. The major losses due to friction in the pipe can be calculated by Darcy equation. So in Darcy's equation, the friction factor is multiplied by L over D multiplied by the velocity head, which is V squared over 2G. Now, if you go back to the curve, you will find that in the x-axis, we have the flow rate, which is Q, and in the y-axis, we have head. So in this equation, we need to have Q, which is flow rate. So we can convert the velocity into flow rate by substituting Q in the main equation. So the volumetric flow rate is equal to velocity multiplied by the pipe cross-sectional area. So the velocity is equal to the flow rate divided by the area. And we know that the cross-sectional area of the pipe is equal to pi d squared over 4. So the velocity will be something like this. Now we can substitute the velocity into this equation. So the equation will be in flow rate form. Okay? We can simplify it further and it will be in this simplified form. Okay? Now how to find the friction factor? We can find the friction factor in the next slide. So to find the friction factor, we need to use Moody's diagram. So in Moody's diagram, we need to find the Reynolds number and the relative roughness of the pipe. The relative roughness is equal to the roughness of the pipe divided by the diameter. And here we can find different pipe roughness values for different type of materials. So we can divide the roughness value by the diameter to get the relative pipe roughness. So we can intersect the Reynolds number with the roughness to get the friction factor. The minor losses due to fittings, how to find them? We can find them using the K-factor method. So the summation of all the K-factors multiplied by the velocity head. As we did earlier, we need to convert the velocity into flow rate. So the equation will look like this. In addition to that, we can add the losses in the equipment. So if we have any equipment in our piping system, we can add it to the equation. So for example, if we have strainers, heat exchangers, or carbon bit filters, we need to add the pressure drop in the equation. So we can find the pressure drop of these equipments from the equipment data sheets or by using real-time data if we have the pressure differential transmitter trend. So we can find the K factor for valves, fittings, and bends present in the piping system by referring to this table. So we can add all the applicable K factors and multiplied by the velocity head. This is how we will get the minor head losses. Okay, now it's time to put everything together. The head of the pump is equal to the major losses head plus the minor losses head plus the static head. The major losses head is calculated using Darcy equation, and minor losses head is calculated using the K-factor method. And we converted both of the equations into flow rate form rather than velocity form because in the system curve we have flow rate, we don't have velocity. And then we can combine both of the equations together. So here we can take out the flow rate as the common factor. Okay, then it will look something like this. So this is our parabolic equation. So HP is equal to the slope of the equation, Q square plus the y-intercept. I guess mystery is solved now. Now how to draw the system curve? We can start by assuming the Q values in the x-axis, and then we need to calculate Q square. After that, we can calculate the constant values, which is the losses, the slope of the equation, which is in red color, the major losses and the minor losses, and then the static head, which is the discharge head minus the suction head. Okay, then we can calculate the head of the pump, and the head of the pump will be the slope multiplied by Q square plus the static head. And we can repeat that for different Q values. That's it. Thanks for watching this lesson on pump system curves. Keep learning and stay curious.